Allowing robots to learn just by observing a human teacher is critical to integrating them into our everyday lives. But how should we go about creating robots that can learn this way? We propose a new approach, taking our inspiration from research in psychology. According to studies of developmental psychology, observational learning can be classified as stimulus enhancement, mimicking, imitation, and emulation. Based on these types, we propose an approach enabling a robot to learn how to perform a task from noisy demonstrations and generalize that task to new environments. Assume that a person wants to teach a toddler how to pour water from bottle A into mug B. The toddler may mimic the teacher by performing exactly the same movements without knowing the results that the movement is bringing about. As long as the conditions are identical, the toddler can perform the task. In imitation learning, the toddler can recognize the purpose of the movement and generalize the task whenever the position of the mug may change. When emulating, the observer does not copy the movement, but recognizes the causal relationship between a teacher's action and the obtained result in the world. In this case, the toddler would be able to recognize what the teacher would do in response to a certain obstacle and apply that same response in a new situation. We can construct robot task knowledge in the same way. Here, we simulate an expert performing a pick-and-place task in a constrained environment by following a fixed trajectory. However, an added obstacle in the environment makes following that trajectory impossible. Therefore, the expert adapts their performance to the new environment. We repeat the same task in many different environments in order to collect a training data set. Our goal is to find a cost function characterizing the entire set of demonstrations. First, an average path is computed from the set of demonstrations corresponding to mimicking and observational learning. Next, in our version of the imitation learning step, we use dynamic movement primitives to scale the mimicking path to a new goal point. We then add a quadratic term to the cost function, penalizing deviations from this previously obtained path. On top of this, we add a Gaussian term weighting the distances to different obstacles in the environment, which we refer to as the emulation component. We learn the parameters of this cost function to explain the entire set of training demonstrations. The Gaussian emulation term allows us to explain every one of the original training examples as a deviation from some underlying trajectory. We can then use model predictive control to compute its trajectory as a solution to the learned cost function. As an example, we show how a UR5 arm can learn how to sweep rubbish into a dustpan while responding to different object classes in the environment. First, the robot is provided with a set of noisy task demonstrations performed in the presence of different classes of obstacles, such as a coffee cup or a marker. Then, the imitation model and the emulation terms for both object classes are computed and combined into a cost function that is used to generalize the task to new positions of the dustpan. As we can see, the robot can adapt to different obstacle positions as well. Although we only demonstrated the task in an environment with one obstacle at a time, the robot can combine the obtained emulation terms into a single cost function and perform the task in the presence of two different obstacles. The proposed approach lets us generalize a demonstration to a new position of the dustpan, as well as to complex new, unseen configurations of obstacles in a new environment, which brings our robot one step closer to being able to learn the way that a toddler would.